Okay, welcome back. Today we're going to be continuing with Chapter 7, dealing with a new type of function. Now, the last couple types of functions that we dealt with a couple chapters ago, for a long period of time actually, we dealt with linear functions, functions that look like lines. Last chapter, we talked about absolute value functions, and those functions look like these. Now, 7.1 went through an activity, an Xbox exponential activity, where we dealt with, we went through and did a little bit of research, did a little bit of math, and we kind of proved or disproved a law that was predicted about 40, 50 years ago, that the speed of computer processing systems would double every 2 years. And that doubling every 2 years was a pattern that we have not talked about yet. And when we graphed it, it looked like a curve similar to that curve right there, like that. So it looked like a curve like that. Now, when we deal with exponentials, they're going to have a curve that looks something like that, or a curve that goes downward from left to right that way. In this case, we're going to be talking about curves that from left to right, they are increasing. And when we talk about increasing curves, they're going to be exponential growth models. Okay? So when we break down this equation, there's a couple of different items that we need to break down. Now, we have our forms, right? We have our standard form of a line, right? Y equals mx plus b is slope-intercept form. Last chapter we talked about the standard form, vertex form for an absolute value function, where there's an a value, an h value, a k value. And this is similar to what we're going to be going to. Now, this is a function that we have not seen really much of it, but let's look at this x value. We have not seen this x value being raised as an exponent, but that kind of goes hand in hand on the name of the model, which is exponential, right? So if we talk about exponential, just remember that the input, or the x, is always going to be in your exponent. Okay, so now we know that our x, is always going to be our input. Okay, we always know that's going to be our input. So whatever we put into our function, okay, is going to have an output, which is our y or f of x or any type of function notation. So that's going to be our output. Okay, we know those two items. Now there's two other items, a and a b, that we have not really specifically talked about with functions up to this point. The a value we have a little bit, but the b value we have not. So when we see the b, let's start with the b value. If we have a number, any number that is raised to an exponent, that b value is usually called the base, right? The big number is the base of the exponent. In this case, the base of your exponential form is going to be, in this case, since we're talking about a growth, it is going to be your growth factor. Okay, it's going to be your growth factor. Okay, now we'll get into that in a little bit more detail, but it's always going to be your number that's being raised to an exponent, and your a value is going to be something else, not your factor, not what you're multiplying every time, but actually what you're starting at. So for our purposes, we're going to call it the initial. Let's go back. Sorry. Initial value. Okay. So we have an a value, which is going to be our initial value. We have a b value, which is going to be our growth factor. So in the activity that you guys just went through, if something is doubling every time, it is being multiplied by 2. So we call it it could be called either the growth factor or the common multiplier, which I will refer to as both. But it's what you're multiplying each time. Okay, so let's go through a couple of examples. Now, let me add just one thing. When we talk about a growth factor, that b value is going to be greater than 1. Okay, so let's talk about a value that's greater than 1. I would say, a 2, right? Or 3.4, right? Or we could talk about 1.2. Okay, these values are greater than 1. Something that's not greater than 1 is something like 0.8, or let's talk about 0.04, right? Something like that. So these would not be considered involved in an exponential growth, but the top would, because that number, that b value, is greater than 1. Okay, so let's go through a couple of examples. So this is exponential growth. Now, just off of what we've been talking about, let's determine whether they are whether they're growth models or decay models. Well, we're looking at, to determine if it's a growth or a decay, we're going to be looking at a growth factor. So we have to look at that growth factor. So if this number is, like I said, above 1, then it's a growth model. Is 0.1 above the value of 1? It is not. So this would not be considered a growth model. Okay, let's look at the next one. Number 2. If we talk about y equals 144 times 1.8 raised to the x, let's talk about our b value. Okay, so our b value is the base of our exponent. So if that value is above 1, then it is a growth. Is 1.8 above 1? I believe so. So this would be a growth. Okay, and the last one, it says y equals 2.99 times, y equals 2.99 raised to the x times 2. Well, this one kind of looks different than the first two, but let's go with our rules. So our base, our b, that's our growth or decay factor, which we're looking at. We're talking about what is being raised to the x. In this case, we have a value of 2.9 that's being raised to the x. And determine if it's a growth model, that number has to be what? Above 1. Is 2.99 above 1? I believe so. So this would be, yes, a growth model. Now let's go back. Okay, so we just determined if it was a growth or decay model. So let's just look at 2 and 3. Now let's kind of break this down a little bit. I want you to tell me what my a value is and what my b value is. So here I have an a value and I have a b value. So the b value is the easier one to figure out. The b value is what is being raised to the x. In this case, 1.8 is being raised to the x. Okay, so our initial value, a, is just our other number that's being multiplied. In this case, it's 144. Okay, good. Now let's look at the last one. Okay, number 3. What is my a value and what is my b value? Like I said, my b value is what is being raised to the x. Okay, in this case, it's 2.99. And my initial value is just the other number, and this is being multiplied by what? 2. The value of 2. Good. Okay, so we just determined whether it's a growth model or not. We'll go into the other model, which I've kind of referred to as a decay model. But let's just focus on the growth model for today's lesson. Now, I determined whether it's a growth or not, and I also determined what the initial value was, okay, and what the growth factor was, so what you're multiplying every time. Okay, good. So now let's talk about writing these equations from a table. So we're going to kind of distinguish, what my initial value is or what my growth factor is. Okay, so now I know I need to have my equation is going to say y equals something, right? But what do I need? I need an a value and I need a b value. Okay, so to determine the a value, if you're kind of looking back to a graph, your A value is your initial value, and your initial value is always where your graph crosses your y-axis. In this case, when your curve crosses the y-axis, what is your x value? Well, your x value is going to be 0. So if you're looking at a table, let's look at the values we're given. We have 0, comma 2, 1, comma 8, 2, comma 32, 3, comma 128. Now, our initial value is where x equals 2. So at what value does x equal 2? Well, looking through our ordered pair of 0, 2, looks like our x value is going to be 2. Or sorry, it looks like our x value is 0, so our ordered pair would be 0, comma 2, and our initial value is just the value of y. In this case, it is just 2. Okay, good. Now let's talk about our growth factor or common multiplier. So that's saying, okay, what do I have to do to 2 to get an 8? Okay, what do I have to do an 8 to get a 32? What do I have to do to a 32 to get 128? Now, I'm going to teach you two ways. The second way is always going to work, but you gotta, the first way you have to kind of think about it a little bit. The second way you just kind of do a little bit of arithmetic. So now you have to think about a pattern, right? What do I have to do each time? And when we talk about exponentials, each output is going to be multiplied by something. So you're going to say, okay, well, what do I have to multiply 2 by to get an 8? Well, 2 times 4 is going to be 8, right? Good. So now let's go down the line and see if that holds true. Well, what's 8? How do I get an 8 to a 32? Well, if I multiply 8 by 4, I'm going to get 32, correct? Good. And let's try it one more time. If I multiply 32 times 4, I'm going to get 128. So each pattern, okay, is consistent that I'm going to multiply each output by 4 to get my next output. So my common multiplier, or my growth factor in this case, is just going to be 4. Okay, good. So now I have an initial value of 2 and I have an initial value of 4. Let's actually change that color just for the fact. Let's go purple and blue. Good. So now I'm just going to take these values and kind of plug them back into my equation. Now, if you remember, my original equation is going to be y equals a times b raised to the x. And remember, whenever I write an equation, I need an y and I need an x. And I need, for this case, I need a starting value, which is my a, and I need a common multiplier or growth factor, which is my b. Okay, so in this case, what is my a? I'm just going to have y equals my a value, which is 2. Okay. Then I'm going to have times my, I'm just going to put this in parentheses, because just to emphasize multiplication, times my b value, in this case, which is 4. Okay, and then I'm just going to raise that b value to my x because I need an x. It's going to look something like that. So my equation for this situation is just y equals 2 times 4 to the x. All right? So that's going to be my equation. Okay, so let's try another one. Now I'm going to do something else. It's another technique that you could use, kind of like the slope formula, but this is something a little bit different. Now I'm going to use a term. In this case, I'm going to use, or actually a statement called dividing backwards. It's just a method called dividing backwards. So if I'm going to divide backwards to find my b value, I am going to take any y value, okay, and divide it by the prior y value. So in this case, I'm going to look at 9. okay? And I'm going to take 9, and I'm going to divide it by 3. Now, the most common mistake is that you're going to want to take the 3 and divide it by the 9. But think about backwards. I'm dividing backwards. So I'm going to take the 9 and divide it by the 3. So I'm going to divide backwards. If you take the 9, you want to look over at my calculator, take the 9, divide it by 3. It's going to give you what? It's going to give you the value of 3, right? So in this case, what is my common multiplier? My multiplier is whatever this value is, you're multiplying it. So you're multiplying this by 3. Let's try it again with 27, okay? Divide backwards from 27. So take 27 and divide backwards. Divide backwards. Okay, so it's going to be 27 divided by 9. So 27 divided by 9 equals 3. So it's a common thread. So in this case, our common multiplier is going to be multiplying by 3. So in this case, I did my b value before my a value. You can do whichever is easier for you. So my b value is going to be 3. Now my b value is 3. What is my a value? Okay, my a value is going to be, remember, where my x value is 0. So if I'm looking back, my x value, I want it to be 0, which is that value right there. So when x is 0, y is what? Y is 3. I'm going to have y as, my purple, y as 3. Okay, in this case, my a value is 3, my y value is 3. That's just a coincidence. That doesn't happen all the time. Okay, so now when I want to write my equation, I'm going to simply take my a value, plug in for a, take my b value, plug in for b. So I'm going to have y equals whatever my a value is. In this case, it's 3. Let's put parentheses around it. Times my b value, which is 3 as well. And that's going to be raised to the x. That's not a great looking x, but you get the idea. Okay, so so all I'm doing, okay, is going to find my initial value where x equals 0, or my b value is, which is either dividing backwards, okay, which is a method, or if you're going down, saying, okay, what can I do to this value to get that value? What can I do to this value to get that value? And you're going to be multiplying something every time. Okay, so I want you to pause the video, and I want you to try number 3. Number 3 is going to be a money problem. And once you're done with that, you can move on to the next part of the lesson. Okay, now the last part is going to go kind of quick because we've done these things before, but I just kind of want to throw some more examples to kind of practice. So whenever we go ahead and graph now for the rest of the year, something that's always going to work is just an input-output chart. So in this case, let's look at the first one. The first one is going to be, let's look at the first one. So the first one is just going to be y equals 2 raised to the x. Now whenever I have an equation or a function, I want to pick a couple of input values. In this case, I'm going to choose 0, 1, and 2. Okay. So now that I have my input values, I'm going to plug them into my function and see what I output. Then I'm going to get some ordered pairs and just go ahead and graph those. Okay, so let me put my input in for x. So if I have 2 raised to the 0 power, what's 2 raised to the 0 power? Anything raised to the 0 power is what? 1. Good. So let's go down to the next value. My input of 1. 2 raised to the first power is 2. Good. And lastly, I have 2. If I plug in a 2 for x, it's going to be 2 squared, which is 4. Okay, now that I have these values, I'm going to go ahead and write some ordered pairs. So the first ordered pair is going to be 0, 1. Next one is going to be 1, 2. Last one is going to be 2, 4. Okay, when I go ahead and plot these, 0, 1 is right there. Good. 1, 2 is right there. And 2, 4 is right there. Good. And now, when we go ahead and draw these graphs, there's a couple of important uh, facts that we need to use before we um, just draw our graph. One, these are always going to look like curves. I refer them to Nike swishes. Now, in this case, this curve is going what? This curve is increasing, so it's going to look something that goes up that way. So when I curve it up, I just want to connect these dots and curve it up and draw an arrow at the top. But what's important is that this curve is not going to cross the x-axis. So I'm going to start it very, very low and kind of curve it up, something like that. Now this value is going to continuously go into the positive direction to positive infinity, and then this direction is going to go positive into negative infinity, but never crossing the x-axis. Okay, that's important for graphing exponential functions. Okay, so the next one, you're going to do the same thing, choose 0, 1, and 2. Just remember, after you raise it, okay, you're going to get a value, then orders of operation tell you to multiply by 2. Okay, so don't forget the PEMDAS. Okay, so this next problem is going to be a money problem. Good luck.